Two batteries in series power a circuit consisting of 4 ohmic resistors. They are connected by a thin copper wire with negligible resistance. Two compasses are placed under the wire at 2 different locations and point north before the circuit is closed. A voltmeter is also connected at 2 locations as shown. For Part A, using fundamental principles, write equations to solve for the conventional current through each resistor. For Part B, find the deflection of compass 2 if compass 1 is deflected by 3 degrees. For Part C, using given electron density, electron mobility, and area, find the magnitude of the electric field through resistor 2. And for Part D, determine what magnitude and sign that the voltmeter will read. The first step in finding equations to solve for the currents through each resistor is to determine how many paths there are in the circuit. This circuit has 2 different paths. Using the loop rule for path 1, we obtain the following equation. 2 EMF minus I3 times R2 plus R3 minus I4 times R4 is equal to 0. Plugging in the given values for the EMF of the batteries and the resistance of the resistors, we get 3 minus I3 times 20 minus I3 times 30 minus I4 times 15 is equal to 0. Doing so for the second path, we get the equation I3 times 20 plus I3 plus 30 minus I1 times 20 is equal to 0. For path 2, solving for I3, we get that I3 is equal to 2/5 times I1. From the node rule, we know that I1 plus I3 is equal to I4. Using the equation for I3 we got on the previous slide, we find that I4 is equal to 7/2 times I3. Now to find the magnitude of I3, we simply plug in the equation for I4 into one of the loop rule equations and solve. We find that the conventional current flowing through resistor 3 is equal to 0.029 amps. Using the calculated value of I3, we can now solve for the currents through resistor 1 and resistor 4. For Part B, we are asked to determine the deflection of compass 2, knowing that compass 1 is deflected by 3 degrees in the northeast direction. Angle of deflection is found by using drag. We know that compass 1 is deflected by 3 degrees. The angle of deflection is given by tangent theta is equal to the magnetic field applied divided by the magnetic field due to the Earth. Simplifying this equation, we get that tangent theta is equal to the current applied divided by I naught. We can arrange this equation to get that I naught is equal to the I applied divided by tangent of theta, which is 3 degrees. Substituting the values for the current and the resistor on top of the compass into the equation, we find that I naught is equal to 1.39 amps. Now to solve for the angle of deflection of the second compass, which is near resistor 4, we plug in the calculated values for I4 and I naught into the equation for the angle of deflection. Using the calculated values for the current applied and the initial current, we get that the angle of deflection of the second compass is equal to 4.2 degrees. For Part C, using the equation for the conventional current, we can solve for the electric field across the resistor 2. Plugging in the given and calculated values, we find that the electric field across the resistor is equal to 126 volts per meter. For Part D, we're asked to find out what the voltmeter will read when it is hooked up to the circuit. The voltage drop through resistor 2 is given by V2 is equal to I2 times R2. Plugging in the calculated value for the resistance and conventional current through this resistor into the equation, we get that the voltage drop through resistor 2 is equal to 0.58 volts. To get the change of potential, we subtract the voltage drop at the resistor from the EMF of the batteries. Doing so, we find that the change in potential the voltmeter will read is equal to 2.4 volts. The voltmeter will read a negative value due to the fact that the negative terminal of the voltmeter is connected to the higher potential part of the circuit.